Understanding the arcing phenomenon requires an examination of how static charge accumulates and discharges within the system. When the flow stops in the pipeline, the fluid is no longer carrying away the static charge generated by the flow. The static charge accumulates on the glass surface of the flow meter and the metal pipe. As the accumulated charge reaches a certain threshold, it discharges through an arc to the nearest grounded object, which in this case is the test bench ground wire. However, since the ground wire is connected to a high resistance ground path, it cannot dissipate the charge quickly enough, leading to the observed arcing. Ground resistance and static discharge are inversely related. The effectiveness of a ground path for dissipating static charges depends on its resistance. The lower the resistance, the faster the charge can be drained away, and the less likely arcing will occur. The National Electrical Code, or NEC, specifies ground rod resistance requirements for electrical safety. These guidelines may not be directly applicable to static discharge situations. However, it is generally desirable to have a ground path with a resistance as low as possible to facilitate rapid charge dissipation. Considering a resistive path for static discharge, the resistance value required to prevent arcing in this application depends on the specific conditions. This includes the amount of charge generated, the surface area of the glass tube, and the geometry of the system. It's a complex interplay of factors that determine the necessary resistance to mitigate arcing. Based on the information provided, it is reasonable to assume that a resistance of less than 1000 ohms would be sufficient to mitigate the arcing problem. However, it is recommended to test different resistance values to determine the optimal value for your specific system. Determining a suitable resistance value requires a systematic approach. Firstly, connect a variable resistor between the flow meter and the ground wire. Secondly, adjust the resistance of the variable resistor until the arcing stops. Thirdly, measure the resistance value of the variable resistor when arcing is no longer observed. This test will provide you with an approximate resistance value that can be used for designing a permanent ground path. In addition to improving the ground path, there are additional considerations to keep in mind. 1. Using an antistatic fluid in the pipeline can reduce the generation of static charge. 2. Grounding the flow meter body directly to the pipeline, if possible, can provide a more direct path for charge dissipation. 3. Installing a bleeder resistor across the flow meter terminals to dissipate the charge can prevent accumulation. In conclusion, to prevent arcing in flow meters, it is important to provide a low resistance ground path for static charge dissipation. A resistance value of less than 1000 ohms is typically recommended, but testing may be necessary to determine the optimal value. By implementing these measures, you should be able to eliminate the arcing problem. The principles underlying static charge generation in non-conductive fluids are rooted in triboelectric charging. When a fluid flows through a pipe, especially a non-conductive one, electrons can be transferred between the fluid and the pipe wall due to friction. This process leads to a buildup of charge on the fluid and an opposite charge on the pipe wall. In the case of a rotometer with a glass tube, the non-conductive oil flowing through the tube can generate a significant amount of static charge, particularly at higher flow rates. When the flow stops, the charge that has accumulated on the oil and the glass tube cannot dissipate quickly, leading to a high potential difference between different points in the system. This potential difference can then discharge in the form of an arc. The factors influencing the amount of static charge generated include the type of fluid, the flow velocity, the materials of the pipe and the rotometer, and the presence of any impurities in the fluid. Fluids with lower conductivity tend to generate more static charge. Higher flow velocities increase the rate of charge generation. The triboelectric properties of the materials in contact also play a crucial role. The grounding and bonding practices play a significant role in mitigating static discharge hazards. Grounding involves connecting conductive objects to the earth, providing a low resistance path for charge to dissipate. Bonding involves connecting conductive objects together to equalize their potential, preventing voltage differences that could lead to arcing. In the context of the hydraulic test bench, grounding the metal base of the flow meter and the steel pipeline is essential. However, the effectiveness of the grounding system depends on the resistance of the ground path. A high-resistance ground path will not be able to dissipate the static charge quickly enough to prevent arcing. The NEC specifies grounding requirements for electrical systems to ensure safety and prevent electrical shock hazards. While these requirements are not directly applicable to static discharge situations, they provide a useful framework for understanding grounding principles. The NEC recommends a ground resistance of 25 ohms or less for grounding electrodes. However, for static discharge applications, a much lower resistance is often desirable. The choice of grounding materials and methods is also important. Copper conductors are commonly used for grounding systems due to their low resistance and corrosion resistance. Ground rods, ground plates, and ground grids are used to establish a connection to the earth. The size and configuration of the grounding system should be appropriate for the specific application. There are different types of static control materials. These materials are designed to minimize the generation and accumulation of static charge. Antistatic fluids contain additives that increase their conductivity, reducing the amount of charge that can be generated. Static dissipative materials have a controlled surface resistance that allows charge to dissipate slowly, preventing sudden discharges. Shielding materials can be used to enclose equipment and prevent electrostatic fields from affecting sensitive components. When selecting static control materials, it is important to consider their compatibility with the fluid and the operating environment. Some antistatic additives may not be suitable for use with certain fluids, and some static dissipative materials may be affected by temperature or humidity. The instrumentation used for measuring static charge and ground resistance includes electrostatic voltmeters, surface resistance meters, and ground resistance testers. The electrostatic voltmeters are used to measure the voltage potential of charged objects. Surface resistance meters are used to measure the resistance of materials to the flow of electrical current. Ground resistance testers are used to measure the resistance of the ground path. These instruments can be used to assess the effectiveness of static control measures and to identify potential problems. Performing a risk assessment for static discharge hazards involves identifying potential sources of static charge, evaluating the likelihood of discharge, and determining the potential consequences of discharge. This assessment should consider the type of fluid being used, the flow rates, the materials of construction, the grounding system, and the presence of any sensitive equipment. Based on the risk assessment, appropriate static control measures can be implemented to mitigate the hazards. In certain applications, it may be necessary to use specialized static control techniques such as ionization or charge neutralization. Ionization involves using a device to generate positive and negative ions in the air, which can neutralize static charges on objects. Charge neutralization involves using a conductive brush or other device to physically remove static charges from objects. These techniques are often used in cleanroom environments and in the electronics industry. The effectiveness of static control measures should be periodically evaluated to ensure that they are still functioning properly. This can involve measuring static charge levels, testing ground resistance, and inspecting static control materials for damage or wear. Any problems that are identified should be promptly addressed. When troubleshooting static discharge problems, it is important to systematically investigate the potential causes. This may involve inspecting the grounding system, testing static control materials, and measuring static charge levels. It is also important to consider the operating environment and any changes that may have occurred. By following a systematic approach, it is usually possible to identify and resolve static discharge problems. Static electricity is generated due to an imbalance of electric charges on the surface of a material. This imbalance creates an electric field that can attract or repel other objects. When the electric field becomes strong enough, it can cause a sudden discharge of electricity, resulting in a spark or arc. The magnitude of the static charge depends on several factors, including the materials involved, the amount of friction, and the humidity of the air. Non-conductive materials, such as glass and plastic, tend to accumulate static charge more readily than conductive materials, such as metal. When two different materials come into contact and then separate, electrons can be transferred from one material to the other, creating an imbalance of charge. This process is known as triboelectric charging. The amount of charge transferred depends on the triboelectric properties of the materials. The triboelectric series is a list of materials arranged in order of their tendency to gain or lose electrons. Materials that are higher on the list tend to lose electrons and become positively charged, while materials that are lower on the list tend to gain electrons and become negatively charged. The humidity of the air can also affect the amount of static charge that is generated. High humidity increases the conductivity of the air, allowing charge to dissipate more quickly. Low humidity, on the other hand, allows charge to accumulate more readily. Static discharge can cause a variety of problems, including damage to electronic components, ignition of flammable materials, and discomfort or injury to personnel. In the electronics industry, static discharge can damage sensitive components, such as integrated circuits, leading to equipment malfunction or failure. In hazardous environments, such as chemical plants, static discharge can ignite flammable materials, causing explosions or fires. Static discharge can also cause discomfort or injury to personnel, particularly in dry environments where static charges can build up to high levels. The human body is a conductor of electricity and can accumulate static charge. When a charged person touches a grounded object, the charge can discharge through the body, causing a shock. While most static shocks are harmless, they can be painful or startling. In some cases, static discharge can also interfere with the operation of medical devices, such as pacemakers. Grounding is the process of connecting an object to the earth, providing a low-resistance path for static electricity to flow. This helps to prevent the buildup of static charge and reduces the risk of static discharge. Grounding is an essential safety measure in many industries, including electronics, manufacturing, and healthcare. The purpose of grounding is to provide a safe path for electrical current to flow in the event of a fault or short circuit. This helps to protect equipment and personnel from electrical shock hazards. There are two main types of grounding systems: equipment grounding and system grounding. Equipment grounding involves connecting the non-current carrying metal parts of electrical equipment to the earth. This includes items such as metal enclosures, conduit, and motor frames. System grounding involves connecting the neutral point of an electrical system to the earth. This helps to stabilize the voltage and prevent overvoltages. The NEC provides detailed requirements for grounding electrical systems. These requirements are designed to ensure that grounding systems are properly installed and maintained. The NEC also specifies the types of grounding conductors that are permitted to be used. Grounding conductors must be made of copper or other approved materials. They must also be of sufficient size to carry the expected fault current. Bonding is the process of connecting two or more conductive objects together to equalize their electrical potential. This helps to prevent voltage differences between the objects, which could lead to static discharge. Bonding is often used in conjunction with grounding to provide a comprehensive static control program. The purpose of bonding is to create an electrically continuous path between conductive objects. This ensures that all objects are at the same electrical potential, reducing the risk of static discharge. Bonding is particularly important in areas where flammable materials are present. In these areas, even a small static discharge can ignite the materials, causing a fire or explosion. There are several different methods of bonding. One common method is to use bonding jumpers, which are short lengths of wire that connect two conductive objects together. Another method is to use conductive adhesives or coatings. Static control materials are materials that are designed to prevent the buildup of static charge. These materials can be used to make clothing, floor mats, work surfaces, and other products. Static control materials work by reducing the friction between objects, increasing the conductivity of the air, or neutralizing static charges. There are several different types of static control materials. Antistatic materials are materials that have been treated with a chemical to reduce their tendency to generate static charge. Conductive materials are materials that allow electricity to flow easily. Dissipative materials are materials that have a surface resistance between 10 to the 5th ohms and 10 to the 9th ohms. Insulative materials are materials that resist the flow of electricity. The choice of static control materials depends on the specific application. In some cases, it may be necessary to use a combination of different materials to achieve the desired level of static control. There are several different types of static control equipment. Ionizers are devices that generate positive and negative ions in the air. These ions neutralize static charges on objects. Static meters are devices that measure the amount of static charge on an object. Ground testers are devices that measure the resistance of a ground connection. Humidity control systems are systems that maintain the humidity of the air at a desired level. Static control training is an important part of any static control program. Training should cover the basics of static electricity, the hazards of static discharge, and the methods of static control. Training should be provided to all personnel who work with sensitive electronic equipment or in hazardous environments. The purpose of static control training is to ensure that personnel understand the risks of static discharge and how to prevent it. Training should cover topics such as proper grounding techniques, the use of static control materials, and the operation of static control equipment. The effectiveness of a static control program should be monitored on a regular basis. This can be done by measuring static charge levels, testing ground connections, and inspecting static control materials. Any problems that are identified should be corrected promptly. Static electricity is a common phenomenon that can cause a variety of problems. By understanding the principles of static electricity and implementing a comprehensive static control program, it is possible to minimize the risks of static discharge. Remember that the NEC guidelines are primarily for electrical safety, focusing on preventing electrical shock and ensuring proper operation of electrical equipment under fault conditions. These codes mandate specific grounding and bonding requirements to handle large fault currents and protect against electrical hazards that could harm people or damage equipment. On the other hand, static discharge control deals with preventing the buildup and sudden release of static electricity, which can damage sensitive electronic components or ignite flammable materials. The energy levels involved in static discharge are typically much lower than those in electrical faults covered by the NEC. Therefore, the grounding and bonding requirements for static control can be different. For instance, the NEC requires low-impedance ground paths to handle high fault currents, while static control often benefits from controlled impedance to allow for a gradual discharge of static electricity, preventing sudden and damaging discharges. The key difference lies in the magnitude of energy being managed and the goals of the grounding and bonding practices. Electrical safety, as governed by the NEC, prioritizes human safety and equipment protection from high-energy electrical faults, while static control focuses on preventing damage from low-energy static discharges.